So last week I tried to prove it, but I couldn't finish it correctly. So I uploaded the uh, additional document giving the proof. So it's you can find it in the canvas. So basically, the problem was you have a two covariate, right? So two weights. One is the using the full covariate, full X. The other one is using the reduced X, X1. So, so your X is a P plus Q dimensional vector, where X1 is a P dimensional and X2 is Q dimensional, right? And then you can construct two different weight. One, so superscript F is the using the full covariate, and superscript R is using the X1 only, right? And and then what you want to show basically is to show this. So this is our goal. So basically, the if you use more covariate, some scaled weight will be higher than some of the scaled weight in the latest model, right? So that's what you want to prove it. And the idea is to use the Gram-Schmidt transformation. So Gram-Schmidt is basically to make it orthogonalized. So you kind of doing a regression of X2 on X1, okay, and compute the residue, right? And so then you can basically so this is X2 tilde becomes the core of X2, uh, ignoring the effect of X1, right? I mean, adjusting the effect of X1. So that's supposed to be orthogonal. So that is the kind of achieve result by construction, okay, by applying this Gram-Schmidt construction. So basically, if you look, this is a regression coefficient for the regression of y x2 on x1, right? For the regression of x2 on x1, essentially. Okay, and then once you do that, then you can actually consider a one-to-one transformation from the original x1, x2 to x1 and x2 tilde. You can find this document in the canvas. And then this guy has an inverse. And you can check. So if you multiply this one to this one, you can get a diagonal matrix, right? So this should be inverse. So that means you can actually, so by the way, this guy, if you work out the algebra, you can obtain this. And then apply this kind of a trick. And then gxi is x tilde, right? I mean, if you let me see, right? Gxi is x tilde. So basically you can get x tilde. So you can get this result, which is orthogonal. Now x tilde. So x tilde is the same column space of the x, but they are orthogonalized. So that you can actually so this guy can be, so that means this guy is a diagonal matrix. Right? Because the point is this guy is what? Ti times x1i, x2i tilde, and x1i, x2i tilde transpose. So then you have a kind of a matrix, right? And this term is 0. So that means your inverse has a this part is what? This part is a summation of ti x1i prime, right? This one is a summation of ti x2i tilde x2i tilde prime. So that's why you get this here. Okay. So basically this guy is this guy. This guy is this guy. Okay. So I basically work out so write this term Q into two components. And then the first component is nothing but the first component is nothing but the sum of the squares of the regression weight under the reduced model. Second term is non-negative definite. So that you can get this result. Okay. So that is a proof. So so that's that take care of the lemma 2. And then we discussed the soft calibration, right? So soft calibration, we wanna achieve the hard calibration on x1 and soft calibration for x2. And then if x2 is a fixed effect, then it's just we are doing we are using full model essentially, right? So if mu is 0, right? So we have two extremes. One is mu is 0, right? And the other one is so variance of mu. So basically, variance of mu sigma. Okay, sigma u square is we have two extremes. 0, then is a fixed effect. Infinite. No, actually, sorry, the other way. If 0, then that means what? If sigma square is 0, that means u is essentially 0, right? That means we are using x1 only. Okay, so we use calibration on x1 only, but no calibration on x2, right? Completely ignore x2, right? But another extreme is what is the meaning of sigma u square is infinity. Basically, that means we are treating it as a fixed effect. Okay. So so that basically this random effect is somewhere in between, right? So fixed effect means we use a full model, okay. X1 and X2 hard calibration on X1 and X2. That's one extreme. Another extreme is just completely ignore X2, right? And use the reduced model. So soft calibration is somewhere in between. Okay. Right. So this one means that it becomes a reduced regression model. If infinity, the other extreme, that should be fixed effect, full regression model. So then then we can basically so mean part. So this is the fixed mean part. This is a random mean part. This is error part, right? So you have a three component. So fixed mean part you can control as a hard calibration, right? And random mean part, and error part can be combined together to construct the objective function for optimization. And then the weight. So how to find the weight, right? And so that actually has a this lemma. So So we have this problem, and that turns out to have some kind of a rigid type solution, right? So by the way, if you look at this carefully, this is n by n times n matrix, while this one is a p times p matrix. Okay, because x is n by p, and so this guy is p by p. This is p. So usually, so that means this one involves inverse of the n by n matrix, while this one is inverse of p by p matrix, right? So second term is easier, generally speaking. So n can be like 1,000, right? The 10,000. P is just 10 or 20, right? And so this should be much. Second part, it should be much simpler. So okay, and then once you use this formula, right? Once you plug into this formula and apply to your weight, then you can write it as something like this. And then interesting part of this message is that if you set a gamma to infinity, then it's just reduced to the regression weighting, right? Regression weighting, which is obtained by minimizing this one subject to the constraint. And so what does the message here is actually you can solve the constrained optimization problem by solving unconstrained optimization problem and let this gamma So this part, this part is really large, right? If this part is gamma is really large, then finding the minimum of this q omega should be that makes this one the first term equal to 0, right? Because this one is infinity. Then how can you find the minimum of omega? That means you should make this one to be 0, right? So this is infinity. We want to find the minimizer, right? Minimizer of omega. And we know that gamma is infinity. That means this one must be 0. Okay, right? So that means you can actually solve constrained optimization using unconstrained optimization if you use this trick. Okay. So that's one kind of interesting. And then this idea can be actually used to solve our soft calibration problem, because now if you write the whole everything, right? If you write, so previously we separate our C and D and make C equal to 0 and D minimize the square expected of gamma D square, right? So previously we have this decomposition and make C equal 0. That means we use constrained optimization. But now we know that constraint optimization can be solved by unconstrained optimization, putting additional tuning parameter for C part, right? So that means we can actually do the same thing here. So we can make introduce a tuning parameter gamma 1 to control the hard calibration constraint, okay? And we let gamma 1 to infinity later. So then everything becomes so the whole thing becomes unconstrained optimization, right? And then all you have to do is to let so solving this one this is a quadratic function, right? Quadratic function of omega. So quadratic function of omega, you can solve it by using some kind of least square method, supposedly. Okay, so you can solve the least square method to obtain this solution, and then you can move this to infinity, right? Because you want to achieve the hard calibration on x1 part. So then you can control. So that is your final solution. And then we can check that this weight achieves hard calibration for x1, but not soft calibration for x2. Okay. Another way. So this is optimization with respect to omega. But you can actually directly use this relationship to obtain omega infinitely. So this is another way of obtaining omega using prediction. Because it's the same thing, right? I mean, how did you compute the regression weight? The regression weight was obtained by solving, right? So you could compute theta hat, right? And view it as a linear function of y, and then so right, you first compute this one, and then we know that beta hat is a linear in y, so then you can actually obtain a weight, right? So the same thing. So here, this is normal equation for obtaining beta regression coefficient on the mixed effect model. So that the normal equation for mixed effect model is sometimes called the Henderson formula. Is it looks familiar, or is it totally new? It should have been covered in 511, right? No? Raise your hand. Are you familiar with the Henderson formula? Mixed effect. Nobody? Probably heard. So where did you get this? Where did you get this? Mixed effect, right? 510, right? Yeah. It should be, right? Because you have basically I don't, well, what is the implication of this one, right? If you think about the likelihood, you have suppose you have a normal, right? It's suppose that everything is normal. You have a kind of exponential of the whatever, sigma e square y minus x beta, x1 beta minus x2 u square, right? So this is the conditional model. I mean, conditional on y on given x1 and u, right? And then you need to multiply sigma u square d square, right? I mean, if this is depends on how you so you have a random effect. I mean, randomness here, right? Sigma u square. This is, suppose this is I, then you have this. Otherwise you will have something like this is to u prime t inverse u, right? So this is you can view it as if you are Bayesian, then you can, this is essentially prior, Gaussian prior. But in the random effect, this is just a random. I mean, you have and so you so this is y given x and u, and u given, right, u given x. So this guy comes here, this guy is here, okay. And then you can basically, the Henderson formula is basically treat beta and u as fixed effect and solve. So that is this guy comes in. You have this one. So so that is the well, this is kind of advanced, probably too much for 521. But nowadays, if you want to write a paper, you have to, you know, I mean, so for example, here, so soft calibration. So published in Biomatica, very recent, right? I mean, so yeah, so this is, so these two papers about soft calibration in the context of causal inference. This is these two papers, soft calibration paper in the context of survey sampling. So you can see that survey sampling is earlier, right? But published in less prestigious journal. So Biometrica. So if you write a paper, same topic, if you write it in terms of causal inference, you can publish it Biometrica. But if you write it in terms of survey sampling, then you can probably publish it JSPI. I don't know, I'm just kidding. But anyway, but I think so you can see that the statistical principle or the concept has a common, but they can be expressed differently in different contexts. Okay. By the way, let me finish up this. Okay. So if you, so this gamma 2, right, is a plays the role. So this is kind of sometimes called signal to ratio, signal to noise ratio, signal to noise ratio, right? So the signal of the random effect to the white noise, right? It plays the role of tuning parameter. And we can estimate it from the restricted MLE, right? You can restrict MLE is a kind of profiling out beta and try to maximize the variance component. So that's one way. Another way is using k-fold cross validation. So how can we use k-fold cross validation? The idea is, end of the day, this will create a compute prediction, right? Prediction in terms of tuning parameter. So your prediction is a function of a tuning parameter gamma 2. So then you can actually use separate the sample, right? And so you use the k-1 sample to estimate, to compute YI hat. I mean, estimate the parameter. So basically beta hat, right? Beta hat, mu hat in terms of gamma. And then use that to compute the prediction here, right? In the task set. So So this is a training set. Use the training set, given the gamma 2, right? Given the tuning parameter, you can solve this mixed effect, Henderson's formula to compute the beta hat and mu hat, and that will give you a prediction. So that will give you prediction given gamma 2. And then nice thing about this one is that you have in the test sample, you never use the test sample to estimate parameters, right? So you are kind of innocent. So then you can actually compare, right? You can actually compare. You have observation, and also you can compute the prediction and compare, and then find the minimizer, right? Minimizer in terms of the mean square error or something like that. So that's the idea of the k-fold cross validation. So I already covered this. Soft calibration and causal inference context is I think this is still there's a still so soft calibration is nothing but L2 penalization using L2 penalty term. But you can use L1, right? Or other model selection criteria. Then the theory is behind all this it's not fully investigated in the literature. So I think this is a promising area of research. Okay, that's for